So today we're going to put into practice all these aromatic substitution reactions that we learned how to do. The first thing we're going to do is to focus on following these aromatic substitution reactions. I mean, if I give you a list of reagents here, you should be able to tell me what the product of these reactions are, okay? And to be clear, we want all possible products. All right, so basically today we're just going to do a whole bunch of example problems. We're going to focus first on following these reactions. So if I give you a series of reagents, you're going to tell me what our product is. And then we'll work on the sort of synthesis where if I give you a beginning and an end point, you got to fill in the middle there. Okay, but let's work on first following these aromatic substitution reactions. So everybody take a minute and see if you can't fill in the products for these two reactions here. so let's go through these here. Oops. This first reaction is going to add what to this ring? A nitro group, an NO2. So now my second reaction, in order to tell where that substrate is, where that electrophile, that bromine is going to go, I need to be able to classify my NO2 as either orthopara or meta-directing. That nitro group is which one? Meta. So that means it's going to direct to these incoming positions. Either one would give me the same product. So my bromine will be meta to that nitro group. All right. This first reaction is going to create what product? Do we actually know the name? What's up?
Real quick, on the test, is it fine if we just write out NO2, or do you want the entire Lewis structure?
No, I don't care if you write out NO2. That's perfectly fine. Your homework system doesn't have that option, so you got to do the Lewis structure every time. NO2 is perfectly fine on an exam. All right, that first reaction creates what product? We know the name of that one. Oh, so just the first reaction, sorry. Ethylbenzene, right? We're going to have that ethyl group on there. Okay? This is that Friedel-Crafts alkylation reaction. Oh, I get it. Everybody was giving me the first. I get it. Okay, anyways. Yeah, so the first step of the second reaction, I should have said, gives us ethylbenzene. Cool, and then I'm going to look at this ethyl group. This is what? Orthopara or meta-directing? This one's orthopara, which means it's going to direct to both the ortho and the parasite. So when I do my next reaction here, I'm actually going to get a mixture of these two products with that sulfonic, one with that sulfonic acid group in the ortho position, and the other with that sulfonic acid group in the para position. And again, I'm cool with SO3H on an exam. All right, so first of all, when we're talking about all possible products here, really what we're making sure to pay attention to is whether that first substituent is orthopara or meta-directing. If it is orthopara-directing, we're going to have a mixture of these two products here, so we're going to draw them both because we're drawing all possible products. All right, cool. So those were when we do two of our aromatic substitution reactions. Now let's throw a third one in the mix here. Okay, so take a minute and give me the product of these two reactions here. right, so this first reaction is that Friedel-Crafts acylation reaction. All right, I'll add these 1, 2, 3 carbons to my ring, attaching it at that carbonyl carbon. I'm now going to do my next reaction here, which adds that sulfonic acid group. But I got to look at what's already on the ring and ask myself, is this an orthopara or a meta-director? So this thing right here is which one? Meta. Anytime we have that carbonyl carbon next to the ring, that is a meta-director. Right, so it'll direct that incoming substituent to either of those two meta positions. They're identical, so I only have to draw one. All right, cool. But we're not going to stop there. We're going to do yet another reaction. I guess we established this one was a meta-director. So this one wants to direct, that acyl group wants to direct that incoming substituent to the position that is meta to it. But then I also got to look at my other group on that ring, that sulfonic acid group. And that is what? Orthopara or meta-directing? That is also meta-directing. So it wants to direct the substituent to the position that is meta to it, which would be here, which is occupied, so that can't happen, or here. So in this case, both of these are in agreement, so they're both going to direct that incoming chloro group to that bottom carbon. We got no conflict here. They are both in agreement as to where that next substituent should go. All right, so now let's do this next one here. That first reaction, we'll put a nitro group on that ring. And that nitro group we said was meta-directing. So we'll direct to one of those two meta positions. Again, they're identical, so I just have to draw my one product. All right, but again, we're not going to stop there. We're going to do another reaction. So now we have to look at both of those groups. The nitro group we said was meta-directing, so it wants to direct to that only open meta position. But what about the bromine? Is it orthopara or meta-directing? Orthopara. And so if we look at the positions that are orthopara to bromine, that would be the ones right next door. Those are the ortho positions. Or the one on the opposite side of the ring, the position para to that bromine. So now we have a conflict. The nitro group wants to put the substituent somewhere. The bromine wants to put the substituent somewhere else. So where is it going to go? Now we can't just compare these two in terms of orthopara or meta. We have to look at their ranking. Right? Remember, not only did we assign each of these groups to be orthopara or meta-directing, we also created this hierarchy. Let me get rid of some of these colors so this doesn't get too busy. All right, we created this hierarchy of strong, moderate, and weak orthopara directors, and then moderate and strong meta-directors. Right? So when we have a conflict, how are we going to break that conflict? We have to look at the relative strength here. All right? So what we're going to do is not just say that this was a meta-director, but that nitro group is a strong meta-director. And our bromine is orthopara, but it's what type of orthopara director? It is a weak. So which one's going to get their way? The strong one or the weak one? The strong one's going to win, right? So that stronger group is going to be the one that directs that incoming substituent. So in this case, that incoming methyl group will be placed meta to that nitro group. Okay? So when we're adding a bunch of stuff to our ring here, maybe those two groups are in agreement. Like in this first example, they're both like, yeah, put it in the meta position. Great. However, we can have a conflict between these groups, and that's where that ranking that we discussed comes into play, right? The stronger group wins. That's our principle here. Cool, so then last class, we complicated things by discussing reactions that we had already actually discussed before, but sort of highlighted them and put them in a special group, because these were our reactions that would convert orthopara into metadirectors, right? So these are reactions that you would perform on the substituents that you added to our ring here. We had these 4 reactions. We covered them throughout these various 2 chapters, but we kind of took a minute to summarize them as being important, because again, they will convert from orthopara-directors to metadirectors or metadirectors to orthopara-directors, okay? So these are not the electrophilic aromatic substitution reactions we've been mixing and matching, but they're still very important for this chapter. Cool, so let's practice using those. All right, so let's do this one. That first reaction, first step is going to put a methyl group on that ring. That methyl group is an ortho-para director. So it's going to direct incoming substituents to the ortho and para positions. So I'm going to have to draw both products of this second step. Let me make a little bit more room for myself. Okay. My first one will have a sulfonic acid group in the ortho position, and the second one will have that sulfonic acid group in the meta position. Okay? Then I'm going to do this third reaction here. And this third reaction is using an excess of NBS, which is one of our benzylic position reactions. That will brominate a benzylic carbon. So my toluene here is going to go from being a CH3 to a CBr3. If you wanted to write that CBr3, I'm cool with that as well. All right, same thing. And previously we said that this was an ortho-para director. But as soon as we brominate that position, this isn't going to be an ortho-para director anymore. This is one of our meta directors. Okay? So now when we're going to do our last reaction, we have to compare our two substituents here. This big ugly thing here is a meta director, so it wants to direct to this position and this position because that's meta to it. And what about my sulfonic acid group? Also a meta director, but it wants to direct to the positions that are meta to it. So that would be those purple positions there. So now we have a conflict. All right, and so how are we going to resolve that conflict? We got to go to that strong, moderate, weak business. That tribromo methyl group there is a strong meta director, whereas that sulfonic acid group is only a moderate meta director. So that means that my brominated carbon is going to win. Whoops. Let me make a little bit more room. So it's going to direct to those meta positions. They are not identical. So I'm going to have to do one product with a chlorine group in one meta position and another product with the chlorine group in the other meta position. And then I have to play the same game with my other product here. We have the same conclusion about this being a strong meta and this being a moderate meta. But again, the positions that are meta to them are different. So this are my one removed meta positions from the sulfonic acid, whereas this is my meta position to my CBr3. And again, the CBr3 is the strong one, so that's going to win. In this case, they are two identical positions, so I'll only get one more product. Okay? So in this reaction, when we did this third reaction, this third step here, we converted our ortho-para director into that strong meta director, and that strong meta director then took over and dominated what the product would be in that fourth step. Cool. All right, let me make some room here. All right, so this first reaction is going to put a bromine on the ring. Bromine is ortho-para. So that next reaction is going to direct to that ortho-para position. All right, but again, these aren't identical, so I'm going to have to draw two. I'll have one with my nitro group in the ortho position, and the other with my nitro group in the para position. All right, so now we're going to carry out our next reaction here, and these are actually a package deal, a two-step reaction. All right, this is how we convert that nitro group into aniline, right, into an amine group. So after this step here, I'm going to change my nitro group from being NO2 to NH2. So then my last step here is an acylation reaction, but I gotta look. I have my bromine that we established was an ortho-para director, so it wants to direct to those green positions. That amine group is what? Also ortho-para. So it wants to direct to its ortho and its para group. And which one's going to win here, the bromine or the amine? The amine. The amine is a strong ortho-para director, whereas bromine is a weak ortho-para director. In this first product, those two sites are not equivalent, so I'm going to have to draw both products. All right, on this one though, they are equivalent. That's molecule symmetric, so I just have to put that acyl group on one of those two carbons. So again, we're going to get these three products here. All right, cool. So the first thing we should be able to do is to follow all of these reactions step by step here. All right, but now let's do something that's a little bit more challenging, which is to try to predict our pathways. So not just following, but predicting our pathways here. Meaning I'm going to give you a starting point, and 99% of the time it's going to be benzene. And I'm going to give you an ending point, and you're going to tell me the steps that we need to do that. How do we get from A to B on this one? All right, so when I look at this product here, I want to sort of try to think of the reactions that I can do that would put that particular substituent on that ring. So a sulfonic acid group, how do we do that? All right, that's using our fuming H2SO4. Okay, so if you remember at the beginning, we introduced these reactions, and I was like, you really want to know these reactions here, right? Because all we're going to do is mix and match them and all that jazz. So when I see an SO3H group on that ring, I need to immediately know that this is the way to do it, right? I need to know what reagents that I need to put on that to put that on that ring. Likewise, my bromine, I'm going to use a different reaction. I'm going to use that bromine. And you can either use aluminum bromide or iron 3 bromide. Either one would be fine, but we got to have that catalyst in there as well. Okay, so here are my two reactions. The question is now, what order do I do these two reactions in? All right, so I want to look in my product here. Are these two groups orthopara? Are they orthopara or meta to one another? They are para. So that means the first thing that I need to put on that ring needs to be an orthopara director, right? So that first reaction I'm going to do is this bromination reaction, because that's my orthopara director. And then the second reaction I'm going to do will be that fuming sulfuric acid, right? If I tried to reverse these, I would have that bromine in the meta position. I don't want that. What's up? No. That's a good question. So you would use a blocking group if there was some gigantic bulky group that was blocking the ortho position here, okay? You will get a mixture of both products, the ortho and the para products. But remember your laboratory techniques. We have like a billion techniques for separating stuff out when we get a mixture. So my question is, what pathway will lead to this product? There may be something else in that mixture that we gotta chromatography out of there or something like that, but you just need to propose a pathway that would lead to this product here. It may be one of many, but just a pathway that leads to that product, okay? Importantly, you couldn't do this in the reverse direction or you wouldn't get any of this product, right? That's the bottom line. Okay, cool. So now we have another one here. And again, we just need to look at these substituents and think of all the different ways that we know how to make these substituents here. All right, so in this case, the sulfonic acid, the only thing we can do is that fuming H2SO4. All right, for a methyl group, that would be a Friedel-Crafts alkylation reaction. So we could use chloromethane and aluminum chloride. And then lastly, for that chloro group, the way to do that is chlorine and either aluminum chloride or iron chloride, iron 3 chloride. Since aluminum chloride is a catalyst for so many of these electrophilic aromatic substitution reactions, you'll see me use that one a bunch. It's both the catalyst in our Friedel-Crafts and our halogenation reactions, but again, you can use the iron 3 chloride as well, FeCl3. All right, but again, I gotta think about what order to do this in here. These are all spaced out one apart. It's not really correct to say that they're meta because there's 3 substituents on this ring, but they all got that meta-like spacing, right? If I look, my alkylation reaction is orthopara. So if I did that one first, I'd be putting substituents here, here, and here. Well, there's nothing there, so I don't want to start with that one. If I did my chlorination reaction, this is also orthopara. And if I look, there is nothing orthopara to that chloro group. All right, but if I look at my fuming H2SO4, this one is a meta director, and indeed those two are occupying that meta site. So the first thing I'm going to do is my fuming H2SO4. Then I can do actually either of these two reactions. You could do in either order here. You could either do the chlorination first, and then the Friedel-Crafts alkylation. You could have reversed steps 2 and 3. That would have been perfectly fine as well. Either one of those would have been correct answers. Okay. Importantly, what helps you out here is that this is a moderate meta director, whereas these are both weak. So regardless of which one you put on the ring first, it's not going to overtake that meta directing of that sulfonic acid group. Okay, we will pick up with this example next time. I just want to say real quick that I have a feeling a lot of people are tempted to say that this reaction here would be a Friedel-Crafts alkylation reaction using something like CH3, CH2, CH2, CH2Cl, and AlCl3. I think you're forgetting about the fact that these alkylation reactions go through these carbocation intermediates. So there's no way for you to stick a primary carbocation on that ring. It would undergo a hydride shift. Okay, so anyway, we had a way of dealing with this, and we'll pick that up next time. All right, we're going to do a few more examples of our aromatic substitution reactions next class, and then we'll sort of jump into general review. Somebody had a question? What's up?
What if you have like a weak constant here and a weak meta?
Don't worry about it. I won't throw that at you. Truth be told, you would get a mixture of everything then. No, that's not on our study guide. So there is a study guide posted, but it picks up with chapter, yeah, whatever it is. Yeah.